In my previous video, I talked about the data preparation part for my credit risk modeling. In this video, I'm going to talk about the modeling part for my credit risk model. First method I'm going to use is logistic regression. Logistic regression is a statistical method used for binary classification tasks, where the goal is to predict the probability that an input belongs in one or two classes. For the logistic regression, the first step is linear combination. That is, we have all those input features x1, x2 to xn. Those are independent variables, and we are going to combine them linearly to generate this logit. And the next step, we are going to use this logistic function Sigmoid, and we will put this logit here and build our logistic function. Then we are going to train our model. Lastly, we are going to decide the decision boundary. Usually, a common threshold is 0.5. So first, we will decide this linear model. Here, we only have one independent variables. Of course, you can have more like this. And then we are going to use this Sigmoid function, and the output will look like this. So if we have two classes, one class we call it class 0, another class called class 1, and then you can see from here, let's say 0.5. If it is over 0.5, we will say this data point will belong to class 1. If the value is below 0.5, we are going to say this data point belongs to class 0. Logistic regression is a simple yet powerful algorithm for binary classification, and it is interpretable as you can examine the coefficient to understand the impact of each feature on the prediction. Like I mentioned before, those features are represented with independent variables when we do the linear combination. And logistic regression assumes a linear relationship between the features and the log odds, which may not always hold in real-world scenario. In such cases, feature engineering or more complex models may be needed. Lastly, logistic regression can be extended to handle multi-class classification problem through technique like one versus all or Softmax regression. I have another video in my YouTube channel talking about the differences between Sigmoid and the Softmax activation function. If you haven't watched that video, you are welcome to watch that video as well. After we build our model, we need to evaluate our model performance. And there are several concepts we have to understand when we want to evaluate our model. First is precision. Precision equals true positives divided by the sum of true positive plus false positive. Precision is a measure of the model's ability to avoid making false positive predictions. Precision answers the question of all the instances the model predicted as positive, how many were correct? The second measure we usually use is called recall. Recall equal to true positives divided by the sum of true positives plus false negatives. Recall quantifies the model's ability to capture all relevant instances of the positive class. Recall answers the question of all the actual positive instances, how many did the model correctly identify? There is often an inverse relationship between precision and recall. As you increase one, the other may decrease. Next concept is called accuracy. Accuracy equal to the sum of true positives and true negatives divided by total number of predictions. Accuracy provides a straightforward measure of a model's performance by indicating the proportion of correct predictions out of all predictions. It is often expressed as a percentage with higher values, indicating better model performance. Lastly, we have F1 score. F1 score equal to 2 times precision times recall divided by the sum of precision plus recall. F1 scores range between 0 and 1, which higher values indicating better model performance. A perfect model achieves a F1 score of 1, indicating both perfect precision and recall. When precision and recall are imbalanced, the F1 score is a more informative metric than accuracy. Let's take a look at this confusion matrix. On this side, we have the actual class. That means this is a positive in the data sample, and this is negative in the data sample. And also we have predicted class. That means our model thinks those data points are positive, and our model thinks those data points are negative. And so, if both are positive, we call it true positive. If the actual data point and our model data points consider the data points as negative, we will say that's true negative. If it is positive, but our model thinks it's negative, we call it false negative. Similarly, we will have false positive. So precision is considering this role. That means we use true positive divided by the sum of true positive and false positive. And we have other measures like sensitivity, specificity, and we have accuracy here. I have another video talking about the confusion matrix for machine learning in my YouTube channel. If you haven't watched that video, you are welcome to watch that video as well. Next method, I will use random forest classifier. A random forest classifier is a machine learning algorithm that belongs to the ensemble learning family, specifically designed for classification tasks. Let's take a look at the advantages of random forest classifier. Random forests are known for their high accuracy and are less prone to overfitting compared to individual decision trees. And they handle noisy data well and can work with both categorical and numerical features. Random forests can provide information about feature importance, which helps in feature selection and understanding the data. Also, building individual trees can be done in parallel, making them computationally efficient. Let's take a look at those steps we need to take when we use random forest classifier. First, in random forest, n numbers of random records are taken from the data set having k number of records. Then, individual decision trees are constructed for each sample. And then each decision tree will generate an output. Lastly, final output is considered based on majority voting or averaging for classification and regression respectively. The last method I'm going to use is XGBoost, that is extreme gradient boosting. It is a popular machine learning algorithm that is widely used for supervised learning tasks. In XGBoost, we have several trees, but instead of building those trees independently, trees are produced in sequential order, with each tree trying to fix the errors of the previous trees. And for a model, we are going to use k-fold cross-validation to validate our model. We divide the total population into 5 equal samples. Models are now trained on 4 samples, the blue box. For example, in this case, we use those data as training set and use this, the yellow box, to do the test. So we will validate on one sample, this yellow box. And then we switch it over. We use the second block as a test block for all other 4 blocks as a training set. And we will repeat the same method over and over to loop through the samples. Once we have all 5 models, we average the error terms to determine which one is the best. Now, let's go to Python to implement our model and check out the result. I will upload this Python code into my GitHub so you could download it and try it by yourself. First, I'm going to load this dataset. About this dataset, I already discussed in detail in my previous video. If you haven't watched that video, it's better for you to watch that video first. And then we'll prepare the data. And then we are going to use this logistic regression to build our model. And then the second method I'm going to use is random forest classifier. And lastly, I'm going to use this XGB classifier. Because for our XGB classifier, there are so many parameters we can use for our model, and I don't know which one is the best. So I used this randomized search CV to search for the best parameter for my model. I put certain option here, and I will call this randomized search CV to search the best parameter for my model, and then I can build our model with those selected parameters. And lastly, I'm going to do this cross-validation. Okay, now let's run our model. Now we got our results. First, we prepared our model, and then we run our logit model. The accuracy of logit model is 0.68. And you can see this is our confusion matrix. You can see the accuracy 0.68 is right here. True label is on this y-axis. That means this is actual value of the data. This predicted label is our prediction from our model. So if this is 0, match the true label 0, means it did a good job. So over 3,200 the model predicted correctly. And for 1 over 800 data points, we predicted correctly. As I mentioned before, precision and recall has inverse relationship. So when recall is small, precision will be high, and vice versa. So for the logistic regression, the best data point is 0.49, about 0.5. For our random forest classifier, we have accuracy 0.79. So this is better than this logistic regression. And for this XGB classifier, we have accuracy 0.81. So it's even better. And also we can check this true label versus predicted label. And also we can check the precision versus recall in our XGB classifier. It looks like this. And the best point should be 0.52. And as I mentioned, because I want to find the best parameter for our XGB classifier, I just use this randomized search CV, and then after search we got those best parameters for my model. And then I run the model, and also I did cross-validation. The mean of the score is 0.81. So this is pretty good for our model. This is how I can use the credit data I showed in my previous video to build credit risk model. Please provide your comments and subscribe to my YouTube channel. Thank you.